interconnect, so we can talk to our magnet and control its temperature. We want to be able to do all kinds of control in real time. So we would define all these different pieces of hardware that our machine would need. And then we figured out a way of getting Linux to drive all that stuff. Okay? So what I'm trying to say is there's nothing quite like having a real project to learn this stuff. You know, we started out really not knowing a lot about porting the kernel from one machine to another. I dabbled a little, but never actually had the job of porting the kernel to new devices. And we learned through trial and error. You know, I'm going to go through the material here, but essentially what I'm going to try to tell you is the best way to figure this stuff out, honestly, is to just go and do it. Yes, Chip?
What kind of suit do you do?
Oh, it was a, yeah, actually that's an interesting story as well. It was actually an FPGA, which some people have heard of and some people haven't. It was a field programmable gate array. It was a processor that didn't exist until you turned the machine on and you told the logic gates how to arrange themselves. Okay? People like to use FPGAs to build custom logic. Devices where it's not worth paying millions and millions and millions of dollars to have a custom piece of silicon made. I want to just be able to define my logic and use it whenever I please. You can get these devices that do that. I want to design my own CPU. Okay, fine, I can do that. It's not going to be as powerful as my Intel desktop computer. It hasn't got real silicon powering that CPU, well, there's silicon in there, but in itself it's not a hard silicon product. It's configurable. I'd really like to be able to show that to you. And again, if we do a second session, I do actually have a couple of FPGA boards where we can kind of define our own computer and then build it in front of us and kind of port the kernel to it. And it's all very interesting because it's not even necessarily real hardware. It's a piece of logic. I'm telling it what to be when I turn it on. But this was a PowerPC type device. Okay, this was a PowerPC, so fundamentally not too dissimilar from my laptop, which is also a PowerPC. This is a PowerPC. So, you know, that's a PowerPC 405. That's a Freescale Motorola 7457. You know, who cares about the number? The point is, that's a PowerPC, that's a PowerPC. These are all machines that are related but not the same. As part of the next section here, I'm going to explain to you what I mean by, you know, the difference between one PowerPC and the next. What the hell does he mean? Well, I'll explain it to you. So let me get on to that. I can show you some of these cool gadgets I've got. So what is portability? What does it mean to have a portable system? Okay, so broadly speaking, it means writing software that can be more easily adapted from one machine to another than rewriting the whole thing from scratch. Okay? So, you know, Windows might be portable to this device in the sense that I could perhaps get Windows running on this device faster than I could rewrite the whole of Windows from scratch. But we might not necessarily call that portable. It meets that definition. We want to constrain this a little bit. I think we want to add in a reasonable amount of time to the end of this definition. So, in terms of Linux, I want to have it be the case that a new device comes out, I want to put Linux onto it, and I really want to be able to do that in a matter of weeks, not months or years. I want to be able to sit down and spend 2 or 3 weeks worth of weekends and get the system to a point where it can do something. It may not implement all the features and functionality that I want, but you know, I can boot it and I can say hello world and do some very basic stuff with it. We want that to be reasonably achievable in weeks, not months or years. Okay, so that's portability. Linux has no HAL, it has no hardware abstraction layer like some other operating systems do. So if you take Sun Solaris, okay, they have, depending on the system, they call it ham, hat, HAL. There are different 3-letter acronyms that mean the same thing. And these all mean that I have my core hardware, and I have this kind of HAL layer. I write some code in here, and then my standard system runs on top of it. I don't have to change the main part of the system. I just change a little piece here in my HAL, and magically the new device works. So the HAL's job is to kind of take everything I might want to do and wrap it up in some other function so I could replace that later. Yes, it makes the system very portable. It means that if I have VxWorks, if I have one of these proprietary operating systems that's designed for these kinds of gadgets, yes, it's very quick and very easy to adapt it. It's not very flexible either. So it hinders, if you had a HAL in Linux, it would hinder the ability for you to modify Linux as a whole. You'd have to maintain all these compatibility layers. You'd have to say, okay, so we're a big Redmond company, let's say, and we're going to have this hardware abstraction in place. We're going to have it be the case that you can write a driver now and it's going to work in a few years' time. Oh, but we want to replace that layer with a new one because it's more interesting. So what we'll do is we'll maintain that one, and we'll write a new one, and then in 2 years' time, we'll have another one, and we'll have 3. Every time we make a change, we're going to have to change 3 different places and make the change we actually wanted to make. Now, Linux doesn't really like that. The Linux community doesn't like that idea. It really likes the idea of making changes and not having to care. So that's why there isn't a HAL in Linux. There's no Linux driver model either. Yeah.
Not having driver model or HAL is nice for, as you said, the ability to modify things.
Yeah.
But then it also brings the problem of drivers breaking
Yeah.
into internal versions.
Hence the reason that and also the reason why I cannot use this video out feature on my machine without using a proprietary driver. I don't want to get too much into the proprietary driver thing. I will say that part of my day job is very heavily involved in drivers and worrying about sort of compatibility between one kernel and the next. It's not entirely true that, this statement's not entirely true. So if you go out there and you take an enterprise Linux distribution, I don't just mean Red Hat, take SUSE, take the different enterprise Linux products that are out there. Okay? A lot of those guys try to maintain binary compatibility from one release to the next. So you buy product version 3, okay, and forevermore, product version 3 is going to be set up so that you can take a driver and install it and it will work. Okay? That doesn't mean that there's a stable HAL there. It means that the company is trying really hard not to make changes that are going to break compatibility with drivers for that specific release. Okay?
What I wanted to ask you relating to that was, in some summary of the kernel mailing list, probably the one on Linux magazine,
Yep.
One of the past months, there was this note that one of the committers was sort of working towards
Oh, it's stable.
not quite having a stable driver model, but sort of a surrogate.
What you probably mean is Thomas Gleixner's work on user mode drivers.
I'm not sure.
Okay, I mean, I won't go off too much on a tangent, but there are some guys working on user mode drivers. These are frameworks that enable us to write a driver and have it be like a regular program.
Mm-hmm.
So we already have this for USB devices. We have libUSB there, so we can write essentially a driver as a program that runs and drives a USB device. Yeah, Jeff?
It's a step towards a microkernel.
Right. It's a step towards a microkernel. It's a step towards, you know, MacOS or Linux or something like that. It's not quite that far along, but yeah, it's a step towards saying, okay, well, if we're going to have binary drivers and closed drivers and all these things, we don't like them, but if we're going to have them, let's not have them in the kernel. Let's have them be, that's his motivation. He works in the embedded space. His motivation is to say, we know these guys like to have their binary drivers, their closed source drivers. We don't like that, but if they're regular programs, that's allowed. It's always been allowed to have a closed program.
Right.
So if we can make it somehow so they can do that,
And he has to create an API to be able to do that.
yeah, I'm not endorsing that from the point of view that I think it's a really cool technology. I think that as a concept, it makes it harder for you to use devices in a free way. So maybe we don't endorse that. Yeah.
Not to drive you farther off the top.
That's okay.
But I was thinking about the security implications, but if you're doing drivers in user mode, then that means that whatever protections, whether it's whatever you've done to harden the kernel is actually strengthened, because you're not, with HD more launching this month of kernel bugs and so forth, and just hammering driver vulnerabilities. That would actually be a security plus if you're running it in user space, right? Am I missing something?
Well,
I realize that the portability, and when you get into user mode, you're restricting some things. If from a security point of view, that would actually be an advantage, wouldn't it?
yes and no. I mean, we can. I think we'll have to take that discussion into the part, because there are some real issues with.
I know there's a security alert this morning about something to do with the Broadcom.
Yeah, because
the Windows. That actually came out a couple of days ago. It's kind of been floating around for a while, but yeah, it's a closed driver. It exists for Windows, and there's a known flaw in it.
The alert said that Linux is vulnerable too. It was running an NDS.
Yeah, if you use NDIS wrapper, again, NDIS wrapper basically lets you take a Windows driver and load it into your Linux kernel. Right. You can't use NDIS wrapper on some kernels. It relies on certain kernel configuration options. It relies on 8K stacks, for example, right? It relies on having a larger stack within my kernel, so I can actually call into these functions and not run out of memory to call some of these wireless functions. So some distributions just don't support NDIS wrapper, and you can add it on. Some distributions don't support it, and you can add it. And some now ship NDIS wrapper as part of the distribution itself. So, next slide. Architecture ports, let's get down to it. What's an architecture? Well, an architecture is a fundamental type of new hardware. So, an architecture would be the x86, the IA32 original Intel x86 platform. Not x86 64, not IA64, but the Intel x86. That's the type of architecture. The IA64, the Power PC, the Spark, the Alpha. These are fundamental types of machine architecture, types of processor device. You get families within that. You get families of PowerPC, you get different models of Intel CPU, but they're fundamentally of a unique type. Okay? What does it mean to have an architecture? It means you've defined the language, you've defined what kinds of basic operations this processor performs, specifically, what numbers those are. So when I compile my program and it's converted into binary code, is that binary code going to be interpreted, going to be correctly executed by a specific CPU? Well, I compile it against a specific family of CPUs. So if I built my code for an x86 processor and I'm running it on an x86 processor, that's great. If I'm running it on an alpha processor, it's probably not going to do anything at all, but if it does, it's certainly not going to be what I intended it to do. Okay? So typically what happens is a hardware vendor decides, okay, we're going to create a new type of architecture, and they go ahead and do that. They've got a huge amount of invested interest there in getting adaptation. Okay, they would really like everyone to use that because they just spent a lot of money on R&D developing it. I mean, there's no point developing it if no one's going to use it. Some of us enjoy that, but generally, people want to make money out of things that they have developed. So there's a huge amount of interest here from the vendor themselves, the Intel, Motorola, IBM, in getting support for their new kinds of architecture. You need a lot of funky hardware at this point. You need to have really expensive pieces of hardware with experimental chips on. You need to have all kinds of hardware debuggers, little boxes I can plug into my chip, and I can stop the chip and figure out, okay, what was the next instruction that was going to run. So in the same way you debug your regular program, you can debug the actual instruction by instruction execution of your operating system on your processor. Okay, so that's the kind of tools that they have to have in order to get Linux or any other operating system to work on a completely new